So why don't we go ahead and just get started with the introductions. So we'll get that out of the way, so to speak. So if we can actually go, that's fine right there, Mike. So I'd like to introduce the panelists that we have, the presenters, panelists, and also the participants that are on the call. We have Mr. Mike Wadeson, who is a application engineer over at Telestream. Say hi, Mike.
Hello there. Welcome, everyone.
Okay. He's going to be doing the bulk of the work today, the heavy lifting, if you will, the master of ceremonies as well. Then we got Mr. Lee Whitcomb, SNMP Fellow, and he is an architect over at Imagine Communications. Imagine Communications is a great partner with all of us and have been participating with all the interops, JTNM tests, as well as Mike Wason as well. So as distinguished panelists. And then my co-host is Luann Lindberg, and she's a marketing director over at Telestream. Say hi, Luann.
Hello, everyone. And I think Michael is a SNMP fellow as well, if I'm not mistaken.
He is. I think I'm the only SNMP fellow that's on this, and so I feel very, I don't know, I'm beneath everybody here. And this is being recorded, and there is a question and answer tab if you want to go to the next slide here, Mike. There's a question and answer area. Please use that. The chat window is pretty much just chat, but use the Q&A if you can. This is going to be very interactive. We have enough time to go through your questions and answers. We have a very engaging topic that I think is going to help you with your decisions on how to look at test and measurement. These are some of the conversations we have a lot, and we'll get started here in just another minute. So we've got some time to think about these ideas, play them out a bit. Let's go ahead and go to the next slide, if you don't mind, Mike. And then we want to make sure that you are well informed on these new things that we're working on, not only from a SNMP 2110 perspective, but also just in IP in general, how to look at IP as a new paradigm for test and measurement. So beyond what SDI is doing with waveform monitoring, things like that, what can you do with IP with test and measurement? And we're just at 8:02. So Mike, you want to take it away?
Okay, then. Thanks to everyone for joining us on this next series of webinars. We're going to start with integrity and monitoring of IP streams. So this is confidence monitoring, requiring us to get the right tools in the right locations. And in this presentation, we'll examine the tools available for IP monitoring streams, discuss timing of streams and how to correlate events within the network together as we monitor each of the flows. So within a broadcast network, we're going to guide you through this process in a broadcast network. As the infrastructure or the backbone changes from traditional SDI to IP, most of the ways to produce a program do not change, but the new technologies introduce the need to monitor and measure the signal in different ways. We still will ingest material from sporting events. So we can ingest the material from a live event or a sporting event into our broadcast network. And we might ingest material from program producers, commercial ad spots. It will all come into our main broadcast network. And this material will be processed within the broadcast operation. Maybe we can check the QC to make sure it meets our standards for levels of the audio and the video. Or we might edit that content and put together as a segment or a promo spot within the material that we have, which is served within our data center. And then we might finally broadcast that content to the viewer, either streaming it or transmitting it over the air. And at each of these particular phases, we need to make sure we have the correct levels, that the video, audio are present, the metadata is there, and we've got closed captions and subtitles present within the stream. And traditionally, to do that, we have monitored the video and audio signals to check the presence that they are correct for the content that we're looking at, that there are no pops or clicks when we listen to the audio. Additionally, we'll check the levels of the video are in conformance with our video specifications, whether they be for standard dynamic range or high dynamic range. For audio, we'll also check the audio levels to ensure the loudness compliance, check the phase of the stereo, or multiple channels of audio that combine together to give us surround sound. These ways of monitoring do not change as we move to IP, but how we achieve these requirements does change based on the IP transport and the new tools available for monitoring and measuring the signals. So here in our system, within 2110, the video, audio, and data streams are carried as separate flows across the network. This allows for flexibility in manipulating the video, audio, and data signals in a live production workflow. This is similar to SDI in the workflow carrying audio separately or embedding it within the SDI along with your ANS data. So you can choose to encapsulate the SDI signal with that embedded audio with the ANS data and carry that in SMPTE 2022-6 for transmission across a network. However, we need to manipulate that video, audio, and data signal in our live broadcast. And that means it's more efficient to carry each of these essences separately. And we'll be using Precision Time Protocol, PTP, and the real-time protocol to provide the ability to synchronize these video, audio, and data streams across this asynchronous IP network. The tasks we are going to do in producing a program and broadcasting content do not change. We're still going to have to monitor at the sporting event to make sure we've got the right video levels, that the audio is present. All of those things don't change as we broadcast and shade the cameras at the sporting event or the live event to ensure the quality of the content being sent to the broadcast network. Once it's transmitted and ingest to the broadcast network, we're going to have to monitor at the ingest of this material, again, to make sure the video and audio levels are correct and there are no problems with the video, audio, and data sent from the venue. Depending on how the content is moved through the facility, it could be ingested and stored to a server. It could be sent to our QC operations area for evaluation of the content. It could be edited together to create a program segment, and it could be broadcast or streamed with addition of logo, bugs, and caption. At each of these points, we want to make sure that we have the content correct, there are no errors present, and if it does have an error, we want to be alerted to the kind of problems that have occurred.
Yeah, you bring up a good point there in confidence monitoring, Mike, which is, it's not that the network is unreliable, but we want to take the opportunity to verify what's going on, test but verify. Well, another interesting aspect of this is that even though this is the end result, looking at this from what you're doing in your POCs or setups is learning how to monitor, I think, is vital to this. Lee, did you have some thoughts on that as well? Oh, you're muted.
That would help. Yeah, so also means sort of we'll see later on like having some tools to sort of visualize these connections. And as well, you want to sort of be aware of like detecting faults early. So not just when something's out of compliance, but as if a link is starting to degrade and the power levels are starting to go, and you want to sort of preemptively know that a problem is occurring. So these monitoring sort of will help you with that.
Absolutely. Great. Good points, Mike. Thanks, Lee.
All right. Thanks. So let's now look at how we might start to build up our test system. We might start within the lab in an initial infrastructure. So it's a good idea with this new technology to build some type of test of your initial infrastructure at the start of the process. This helps you to validate your network infrastructure, to provide the proof of concept, to make sure everything will work together as you expect. You'll want to define your reference sender, such as the Imagine Communications SNMP, that provides processing of the SDI signals to 2110 for video, audio, and data streams. Within your system, you want to work out a test plan to validate your workflows and ensure reliability of the system. A good starting point is the JT&M test plan that provides testing of the infrastructure and gives you some idea of the things you ought to be looking out for as you build up the system. You'll also want to validate that these stream workflows with your reference receiver, so you'll become familiar with the workflow and understand the methodologies that are required in this IP infrastructure. Precision Time Protocol, it's the keystone to the IP media network, and we've discussed it in the previous seminar series, the best practices to ensure reliable and robust PTP systems. There's also a good article that Lee wrote that's present in the SMPTE journal for January and February of this year on how to successfully commission a SMPTE 2059 PTP system. So those are kind of things that you can read up about. You can become familiar as you gradually build up this system to evaluate the equipment, To put in your test equipment at appropriate places, you need to start thinking that that equipment is going to be used as you build up this system, as you evaluate things in your infrastructure. Understanding what can go wrong is sometimes key to being able to isolate issues and to be able to quickly troubleshoot the problems. In SMPTE 2110, the video, audio, and data streams are sent separately. So we need to make sure that the receiver subscribes to the correct streams and it has the right IP addresses. We need to ensure synchronization of senders and receivers. And therefore, we need to ensure that PTP is present throughout the network, and we have methods to monitor PTP. In the IP media network, congestion can cause packet jitter, loss of packets. So we need to ensure a reliably designed network and methods to interpret the information for the various streams. Typically, redundancy is deployed within the network architecture using SMPTE 2022-7 that provides duplicate streams of the sender across two different networks. The receiver can then choose which path is best on a packet by packet basis, and we should be monitoring these two paths for correct operation. So these are things to think about that you might not have had to think about relative to SDI, but these are new things that will allow you to troubleshoot problems and understand the technology. Don't forget to check the basics. You'll need to ensure that you're using the correct type of SFP. And sometimes it's difficult to read that label on the front of the little SFP to understand that this is a 10G SFP, or it's a 25G SFP, or it's using 850 nanometer wavelength or 1310 nanometer. So being able to identify the correct SFP, check those things are correct. You've got the right kind of cable for your operation, and you've connected it to the device at the correct port. Sometimes devices won't work in the network is configured and it doesn't have the right IP address for that media node. So making sure you're plugging to the right port, that the port comes up, it has the right IP address and the MAC address for the network. You want to check the device and the switch to make sure the port is active and up. You'll also want to verify the IP address of the port value, and the payload type. These are important characteristics which identify your stream within the network, and you want to make sure that each of those values is set correctly. Another important part, you'll also want to make sure that the TTL value, the time to live, is set appropriately for your network. If it has a value of 1 and you expect it to go through multiple switches to get to a receiver, then that packet will not make it across the network, and you'll be wondering what on earth has happened to your signal. There are likely various configurations in the switch you can use to validate and correctly verify the signal. So you can show the interface status, you can show IGMP snooping for the groups. There are a variety of different conditions that you can set up and probe to get values to check that you have configured things correctly within your network.
You know, it's really, just jumping here real quick, is now that a lot of the devices are supporting LLDP, link layer discovery protocol, as soon as that link comes up, you can typically see the device on the other end doing a show LLDP neighbor, which is great. And that's part of the NMOS ISO4 stuff that's come about, and a lot of adoption from the devices.
Yep. So don't forget to use the tools that are available for you. Once you've started to build out the network, you'll have multiple streams flowing across the network, and you'll want to monitor the reliability of those streams and the network programs flowing through the network at your various monitoring points. You could end up with a large number of streams and a large number of data to keep track of. So in the Telestream Inspect 2110, we are going to monitor by exception. That allows us to focus on the problem events with simple red-green indicators that identify channel issues and make it easy to interpret specific problems with alerts on a channel by channel basis. So quickly we can see we've got 2 channels here that might have problems. We'll get some information related to what kind of alert on a channel by channel basis they have, and then we can dive a little deeper to troubleshoot that particular problem. So we're going to look at this channel here to see what's going on. And so we can drill down a little further and look at the specific channel and alerts that are provided. And the user information within this helps us to identify the type of problem that's present and pinpoint the root cause of error. In this case, we can see that a 2022-7 stream has different signals for path 1 and path 2. By looking at the alert information and by checking the thumbnails of the two streams, our attention is drawn to the fact that this content is different, and these two streams are supposed to be identical. And in this case, they're just not. We're also alerted to the primary and secondary session description protocol parameters that do not match. And this could be another part to our problem. So we can further check the session description protocol PTP that describes the information and brings that up. And we can see that in this case, we've got some issues relative to the different formats that have actually been detected as frame rates for these two particular streams. So that helps us to navigate through the process and quickly identify the type of error that might be present. Here we can see a detailed report of errors from Inspect 2110 that helps easily identify problems within a program. This information can provide long-term trend analysis of the program, so it helps you identify common issues that might have occurred at a specific time or at certain times. And you'll allow the engineer to investigate further to troubleshoot problems within the system. There are a wide variety of tools that can help in troubleshooting issues within the IP media network, and there are lots of analytical tools available within the switch. And Robert's going to describe some of those tools that you can use.
Oh, which is interesting here because now you can use, unlike SDI, which trying to figure out what the stream characteristics are within the switch itself, you have that footprint in the sand capability. So there are a multitude of capabilities on this, which is like we were talking about before, Mike, which is just the interface statistics, seeing that things are flowing, seeing where that multicast is, where you've got the join, looking at the multicast stream statistic itself, how much bandwidth is associated with that, as well as looking when the joins and leaves are occurring, looking where the MAC address is. So this is more like you're learning how to play a piano. You learn all the notes, you learn all the basics, and then after you get all the basics from a command line interface, CLI, we make up acronyms for stuff, right? So the CLI, then that allows you to do things. But if you're not a CLI jockey, then we have tools out there to make this stuff a lot more accessible. We have a tool called Cloud Vision Portal. There are other toolkits that you'll see here from our partners as well as from Telestream. And that allows you to then use a GUI interface to characterize what's going on and over time and historically as well. So we have this thing called Cloud Vision Portal. We call it CVP. We also have something called Multicast Monitor App, or MMAP. And so those are great tools for you to do. But there's also capability to do like a TCP dump, or think of like a Wireshark on the switch itself. So you want to capture the packets or integrate with the Prism to mirror those packets, specific packets, or an entire interface over to the Prism. You just don't want to oversubscribe. You don't want to send 100 gigs over to the Prism, for example. So you want to send maybe just a couple of flows over to it. So a lot of opportunity for analysis here.
Thanks, Robert. And Lee, I believe that there's a lot of alarm and monitoring on our sending devices like the SNMP.
Yeah, so the SNMP is designed to work with in this system here, which has some sort of logging and monitoring system. And so for like every program and every interface via the APIs, you can extract a lot of telemetry. And this is just a small fraction of it, but you've got like on the SDI, is the video present? What the standard is there CRC errors? You can detect issues. On the IP side, you can, are there missing or out of range packets, which can indicate an issue with your network? Path differential on your -7, which can help in debugging -7. On the Ethernet side, you have the FCS errors or optical power level. And these are very useful sort of for preemptively detecting issues. So as your power level is going down, your error counts are going up, you can find errors before they impact you on air. Now with with the SNMP, because we have like 32 channels of video and 512 channels of audio and 128 channels of ANC, there's all the statistics for every single program. So if you multiply it out, there's a huge amount of statistics coming from even just one SNMP. There's also parameters for like measuring the bandwidth, so you can sort of detect if there's issues there. When it comes to on the PTP side, lock status, what the GM is, what the delays are, other ways to sort of help troubleshoot and sort of see is your network and system behaving as expected. And then we also tie into the, sort of the standard syslogging. So if you have a syslog server, we can connect up with that, and you can use sort of your standard tools to analyze the syslog. So lots of different sort of monitoring capabilities there, as well as the sort of GUI and other sort of abilities on the product itself. Next slide. So one thing with the IP networks is they are very dynamic, so you can sort of change your workflow. So having some tools to sort of visualize what is the current workflow, what is the current signal flow, and then to be able to sort of overlay that with where the alarms are, what's the status of different nodes. So there's products like I imagine has the Live Manager or LM Path View and Alarm Console to sort of help you visualize what is your current workflow, which nodes have errors, what are the errors on those nodes. So these are sort of very useful tools because of the flexibility of IP networks. Okay, back to you, Mike.
Thanks very much, Lee. Let's move on now to, as we talked briefly, Robert talked about passing things to Prism. So within Inspect 2110, you can select View in Prism, and automatically the API call is made to Prism that configures the input with specific streams of interest and allows for deeper analysis and troubleshooting the issues further. By quickly configuring the Prism to the same stream that Inspect 2110 was monitoring simplifies this process. Additionally, the information provided by 2110 allow the engineers to more easily pinpoint the issue and investigate the problem further by using Prism. So we can then delve down just by selecting View in Prism. We will then automatically launch the web browser remote BNC application with that specific stream that we were looking at. And we can then go in and identify what was happening. In this case, because it was a duplicate stream with path 1 and path 2 appearing to be different, we can look at each of the individual streams on Prism to make sure that they're error-free. We can check the SDP for the input configuration and ensure that the two streams are the correct flows, which they obviously aren't in this case. And then we'll need to look up, did somebody type in the wrong IP address? Did the sender be set up incorrectly? We can pinpoint and troubleshoot a little bit deeper, but we've been kind of narrowed down our focus to identify the specific errors that we need to look at. And by using this approach, the engineers guided through the process of identifying the error, narrowing the focus, and quickly resolving the issue or problem. Precision Time Protocol is the cornerstone for providing synchronization of timing between senders and receivers across the network. In the previous 3 presentations, we discussed the best practices for ensuring a reliable PTP system within your network, and you can see those best practices from 1 to 13. For instance, in best practice number 10, it indicates we should set the domain value to something other than 0 or 127. And the reason for this is these are typically the default values for a device, and we don't want to put a new device on the network that automatically starts broadcasting and becoming the grandmaster, for instance. So by setting a domain to a different value, we can constrain our network so that some device that's put on the network new that's not properly configured won't impact our reliable network in this system. So if you haven't seen these presentations, then they provide a good foundation for PTP and a detailed discussion of these best practices. Let's take a look at how we might configure some of our systems. And so we're going to set up our reference sender, which in this case is the SNMP. Within this configuration, we'll need to enter a value for the domain. And in my case, I've set that value to be 110. So we need to make sure that is following our best practices, number 10. And so it's not 0 and it's not 127. It's something in a different value range, and in this case, 110. Once we've configured, we will want to check that the system's locked. So we've configured our parameters for announce interval, timeout. We've checked our other values within that system.
Yeah, so I mean, and other things you can also check there, in addition to sort of basic, say, log statuses, things like you may want to look at sort of delay from the master, because that can also indicate that there may be problems in your network. So knowing what is the GMID to make sure you're locked to the correct master, because you have an engineered system. So you want to make sure that the GMID is the one that you expect. So that's a very critical thing to keep in mind. And it's also sort of useful even just like checking what is the current time, just to make sure that a bit of a sanity check there.
Yeah. So I always try and look and see what the last couple of digits of the Grandmaster ID are. I try not to remember everything. And I might remember the first sort of couple of values, which are the organizational unique identifier, which tell me what manufacturer of the device is. So if I can remember those couple of things, then that helps me to identify my Grandmaster, make sure it's the right one. I can go and look it up within my system to make sure it's choosing the primary Grandmaster and not within the system to troubleshoot these things further. But now that I know it's locked to this Grandmaster ID, we're good to go. And I should expect this sender to now be locked to PTP. Now, to ensure stream timing, PTP is used by the device to lock to that reference, as we just saw. It then generates a timestamp value based on a sample of a 90 kilohertz clock for the video and data values, while a 48 kilohertz clock is used for audio. And then we sample that clock and we add that timestamp value throughout the whole of the video frame until the marker bit indicates the next frame of video, and we'll resample the timestamp value and add a new timestamp value into the RTP protocol, the real-time protocol. And that's where this information is carried within each of the packets. So we've got this timestamp value that we're going to send across the network, and then we can use that value to help decode the signal. So let's take a look at how we use this timestamp information along with decoding of the video, audio, and data streams to determine timing and synchronization of the signal. The timing display on the upper right shows the timing relationship between the incoming stream against the PTP reference, and we're locked to PTP in this case. So we've got this reference, and you'll notice it's not exactly in the center, it's offset. And that's because in 2110, we only carry the active video. So we start the timing reference point from this location, which means that it's going to be offset by 21 lines in HD. In 3G, it'll be offset by 42 lines. And in UHD, it's offset by 84 lines. And this is equivalent to the vertical blanking for each of these formats. Now, to illustrate this a little bit further, I've recorded a little video that I'm going to start to play to illustrate how we might look at these values. So over on the upper side, I've got the IP status showing the flows that I've subscribed to. In the lower left-hand side, I've got the timing display. And I'm going to go into the IP status now, and I'm going to sweep across to the other side. And here I can see my RTP clock, which is 90 kilohertz for my video, and 48 kilohertz for my audio. And you'll see the RTP marker frequency, which is actually the frame rate of the video format that we're using at this time, which is 1080p 59p. In the timing display, we're going to be looking to check what our offset is. So you can see it's 41 lines in this particular case. And then the stream timing is going to be used to look at in this minute over a 30-minute interval. And we can see this kind of shape that's got a sinusoidal pattern. That's an indication that there might be a problem with this particular sender. So I'm going to zoom in now to just look at it over 60 seconds. And you can see I've got this kind of glide slope, which is indicative of that sine wave we just saw. So this makes me think that maybe this device might be locked, because I'd like to see a nice linear straight line with little to no variation in my system for this sender. And it don't seem to have this. It's actually glide sloping along. So let me go and check that that particular device is locked. So I'll go and find that particular device. I'll check within the menus. Oh, yes, this device was defaulted to domain 127. And that's our default domain because it just was put online yesterday. And now immediately that I changed it to the correct domain of 110, immediately it started to lock. And so we've changed it from it free running at this particular point to now starting to lock within this particular system to our PTP reference. So this is a way that we can then check and make sure that we actually are locked to us from our sender using PTP. And now when we look at the timing display, we can see it's not 41 lines, but it's actually 42 lines that it's offset. So this device was actually very, very slowly drifting along, and it would have been difficult to tell that without using the right tools to be able to analyze the timing information and then be able to see that this signal now, once it updates automatically in the graph, has much more of a straight line across this 60-second window, which indicates that we've got a good lock now for this particular sender. So that gives you an illustration of how we can monitor the signal and know that this device might not be locked because of its bare stream time, and then we can configure and check it out and make sure it's locked correctly within our process. So that gives you an idea of how you can use these tools to basically ensure your stream timing. And so when everything is then locked together correctly, you should see these nice straight lines in our stream timing display for the video to PTP, which is just this plot graphically of the timing display variations that you see here. The other specific plot, the video to PTP offset, this is a plot of the incoming RTP timestamp against a newly created RTP timestamp that Prism will create based on the current PTP time. So this will give you a calculation of the offset through the network between when the sender sent the RTP timestamp and when we created a new RTP timestamp within this signal. So it's important to monitor PTP within the network, and you can use a variety of tools to check for the presence and the lock of the device. So Lee, in the case of the Imagine SNMP, how would a user check that the device is locked to PTP?
We're just clicking the right buttons here. Yeah, so a couple of things. There's on the alarm tab, if it would generate an alarm if you were not locked. Also, if you go to the reference tab, which you sort of have a screen capture there in the left-hand side, at the top it says PTP lock. So it indicates it's locked there. If you sort of drill down to those details, this is also that same where we were talking earlier, which has the Grandmaster ID. But sort of a very easy summary one is just looking at on the alarm tab. It has the PTP locked, not locked alarm tab. And I said, and that also can be sort of through the APIs fed up to sort of an integrated monitoring control system. So.
Okay, great. So we've now made sure that our sender is locked to PTP, and we can monitor in Prism within the system that our general system through a boundary clock or whatever the PTP messages are making it through. And so we can again see our Grandmaster ID. We get the time information. We get the number of messages that are currently being received for announce, sync, delay request, and delay response. And we can also see the phase lag, which is a kind of indication of how well our system is locked to PTP. And so that provides information graphically also in the Prism, in the PTP graphs, we could further analyze the flow over time. And then for the switch, we've got a variety of different metrics that we can use to obtain from the switch for checking PTP monitoring. And as you can see here, Robert's going to explain, hopefully, some of the metrics that we have for PTP on the switch, like show PTP monitoring and getting the statistics that we have here.
You just did it. You did a great job there, Mike. So you got to just show PTP monitor. Notice also there that we've got this offset for master threshold not configured. So if we see this offset from master and a number comes out that's basically abnormal or out of a boundary, you can actually throw those away. We've seen that with some lower end audio systems. They need very, very tight timing from the switch in boundary clock. And you think of the switch as boundary clock is like a distribution amplifier. I take that PTP in and then I become the grandmaster. So it allows for the scalability. But we can also then take those off values, if you will, where some of the audio devices come out of sync and just throw those away. So a lot of good statistics there. And then again, another screenshot from CloudVision Portal, which gives you that historical thing of, hey, what happened last night at 2 a.m.? Well, if you did a show command right now, that's just point in time, but you may want to get some historical values or over time, like you were showing, Mike, in your Prism, which is, it's more important to know what's going over time versus what's happening in a point in time. Sorry, the reference to time here so much. We're just talking about time all the time, aren't we?
Yes,
Back to you,
indeed.
Mike.
It's the cornerstone to IP. So now we've ensured that we've got our PTP across the network, it's flowing correctly. We're going to move now to look at packet distribution across the network. And this really involves identifying the type of sender that we're using and how it sends those packets across the network. Most gateway devices take the SDI signal as an input and then process the active picture. And those then active picture elements are broken into data segments and then packetized in IP packets. We started at this particular time TPR0. This is our first packet from the first part of our frame of the active picture. And we then start to packetize each of those elements and segment them out and send them as different individual packets all the way through this process until we reach the end of the active picture. And then we'll stop sending packets because there's no more information that we need to send at that particular time. And then we'll have this vertical blanking period before the next active picture, and we'll start this process again. And that forms a gapped packet read schedule. Another type of sender that might actually be used is a linear sender. And so this particular sender will start at the same particular point of the active picture and start putting out its packets, but it will distribute them in a more linear fashion across the whole frame of the video. So it will packetize and distribute those packets even through the blanking interval. So we have this linear approach to this kind of sender. So this identifies our gapped sender or our linear sender within this kind of packet distribution process. Now, in the real world, there's going to be packet variations shown in the orange color here. And those variations will depend on the processing delays inside the particular device. So it might send some packets slightly earlier. It might send some packets slightly later. As you'll see in a moment, we also have another type of sender, a wide linear sender. And this device is based on either a software architecture or a server platform, which has a large amount of variation between when packets are due to be sent and the time that it will take to gather that information from the device, either from a hard drive or a PC bus. Getting that information out may be constrained by the reading of that data, and therefore it may not be ready to send, and then it'll send a whole series of packets in a burst. So this can lead to wider variations in the delivery of the packets. And so we need ways to be able to understand how we can identify these different kinds of senders. And then added to that, the network itself can also introduce jitter into the delivery of the packets to the receiver. Here in this example, we have packets being sent from a sender at regular intervals, but these packets go through multiple network switches and varying amounts of IP media traffic, which can introduce delay between the packets, and this will result in packet jitter through the network to the receiver. So we'd also like to look at that kind of process within the system.
Yeah, Mike, this is an interesting point, and this comes up quite often, which is if you look at your predictable packet pacing, as we call it, and that very, specific way of doing things, we want to make sure that those get through. And people ask us, can I mix post-production with my broadcast network as have it as one? Or if I just have an editing system or playout system, something like that, can I use jumbo frames? And this is a really good diagram here that shows that if you're waiting for a jumbo frame to go through, and you've got these 1500 byte packets, you have to wait for that. It's like waiting for the bus to go through or get off the off ramp or train or to go by or something like that before you send your packet, and you miss out on that predictable packet pacing. So if you're going to mix and match things together, go back to that smallest packet size so you can get this very high valued set of packets in here, and also use QoS as well for the video, the audio, and ancillary data, the most critical of your network packets, if you will. Does that make sense, Mike, what I'm talking about here?
That makes perfect sense to me. And now I'm going to try and illustrate maybe that ways to look at those packet distributions across the network within the Prism device by using a histogram. So typically within our system, we want to analyze the variations that we would have between these packet pacings, as Robert mentioned, and we're going to use the histogram to look at that. So originally we do a graphical plot of the packet interval time. And this will then show us, how many packets we've received within that second interval. And it should be like this, have a fairly nice regular place between those intervals of the packets. Another way that we can actually look at that is to look at it as a histogram. So this actually shows us the time between the various packets. So here we've got a nice pulse where they're all kind of gathered together at one particular place. And here that have been distributed at this interval between some of the other packets. So a histogram allows us to get a characteristic signature, maybe of a device or processes within the network, to identify the types of senders and the types of distribution that we might be having within the system. And so if we look at that in the upper right image, we show a linear sender. This shows the spread of the data around a central peak and with a few outliers at either side. Different linear senders may have a similar spread to this data, or they may be slightly different in characteristics. It's all dependent on the device and the processing through the network. One tip that I typically recommend when evaluating a device as you build up your lab is to connect it directly from the sender to Prism without the network in the middle, so you can see the characteristics of that individual sender. So you'll know of any differences that might occur when you add that sender to the network and look at it on Prism downstream. So this is a way to help you identify the characteristics of a device. And once you become familiar with looking at this histogram and identifying the packet structure, then you can troubleshoot problems within the network. So we'll look now also at the linear gap sender. This gap is effectively the vertical blanking. So we've got all the pulses gathered together over here. And then because there's a vertical blanking, we don't send any packets. And then we start sending packets at the beginning of the active frame. And so there's a clump of packets here, but most of the packets are over here. Now you can use the zoom function within the histogram to go and look inside that larger pulse. But this is the vertical blanking interval. And one of the things that I can tell from this histogram is this is actually a progressive signal. And the reason why I say it's a progressive signal is because there's only one outlier pulse. If this was an interlay signal, I'd expect to see two pulses as outliers, one representing each field of this video signal that would be slightly apart from each other as this gapped area. So you can immediately tell from this histogram, this is a progressive signal, or this is a gapped interlay sender. And then you can verify that by looking at the status bar for the format of the signal. Over here on the right-hand side, we have our wide sender. And so you can see here, this might come from a server. It might come from a device that is a software encoder. And each of those PC devices is reliant on processes within inside the server to gather the data from a hard drive and output it through the system. And all of those processes can vary over time, which might lead to a wider spread of the data across the histogram. So that's got a wider spread of data. Some of it may be more bursty or clumped together. And then there are a number of outliers out to the far right-hand side in this particular case. So that's a wide sender within the configuration. And then over on the far side, I've got a network loop here. And I can tell that because the main peak of this particular transmitted signal is repeated and echoed over a number of pulses as it's looped around. And being able to determine where a loop happened within a network can be sometimes very problematic. So you need to make sure you validate your network to prevent such problems from actually happening in the first place. But this is kind of a characteristic signature again of using the histogram to troubleshoot problems within the network. We've mentioned in this presentation redundant networks based on 2022-7, and there's a sender that provides 2 duplicate outputs that be sent across 2 different networks. As we saw it earlier, it's important that these streams be identical from when the sender is sending that information. And then depending on the network configuration and the loading, these packets will traverse each path slightly differently. And that will result in path differential delay between path 1 and path 2. And then the receiver will make a decision on which packets to choose from path 1 or path 2 on a packet by packet basis in order to assemble the signal correctly and decode the video, audio, and data streams. So here's an example of 2 path 1 and path 2 signals. Path 1 going through the first network, and I've isolated out path 2 going through the second network. And you can see that these are different switches. They have different characteristics to their histogram of sending the data. And then we can see any variations in the path-to-path differential between path 1 and path 2 in this graphical plot over time. So you have a ways to look at these and to check that you are expecting to receive these packets, and then you could isolate down to look individually at path 1 or path 2.
Mike, I think it's important to point here that when you're talking about the different paths, this could be, quote, on the same network, but typically we do air gapped. But this is one of the powers of Prism, because you could use it in a whole bunch of different ways. You've got a couple of interfaces. You could put one on the red side and one on the blue side, or amber blue, or A and B, or whatever you want to call it. And this gives you that ability to say, okay, here's the 2 streams, source and destination, for this. And they're going to have different multicast and different unicast addresses, but you're identifying the streams themselves on each link. I think that's very powerful in terms of what the Prism capabilities are.
Right. Yes. So we have 2 ports, and one would be connected in this case like to path 1, and the other would be connected to path 2. And we can look at them individually, or we can combine those together as any other receiver would do to pick it on a packet by packet basis, the individual streams to assemble those video and audio and data signals together and make sure that we can decode the audio and the video correctly.
Thank you. Perfect.
Okay, so let's move on now to looking at our last particular topic, which is the buffer measurements, which are defined in SNMP 2110-21. And the first of these is the Cmax value, which is defined for the sender. And the best ways to think about these is to think that we have a bucket, and we put our packets into the bucket, but there's a hole in the bucket that drains out those packets at fairly regular intervals. And so our idea is within this bucket, we don't want to actually exceed the value for Cmax. So we won't want to overflow the buffer that a device might have. So we've got a maximum amount of packets that we can put in this bucket. And then we've got the number of current packets that we have at the moment that will allow us to gradually drain out those packets gradually over time. So this is the kind of thing that you want to be thinking about for the buffer kind of measurements, because each receiver has its buffer in order to streamline and align the packets together and make sure that they have a correct flow. So analyzing the buffer, at least within a system, to make sure your device conforms correctly is important. And then in the receiver kind of metrics, we've got VRX full. So again, a similar bucket, except this bucket has a certain capacity, which is going to depend on the buffer size within the receiver, and packets enter and hopefully leave instantaneously. So as soon as a packet comes in, it should be going out of our leaky bucket and being processed by the device. And we'll be putting in these packets into the buffer. And we don't want a case where we're not putting any packets into the buffer and waiting for information. That would be underflow of the buffer. And similarly, we don't want too many packets to be hitting at the buffer, because that would cause overflow and we would end up losing packets from our buffer to realign and assemble that data together. So it's important to look at these metrics to see that our devices meet and constrain our requirements across the network. And within those particular cases, there are defined parameters for a narrow linear, and a wide sender. And you can set up these kind of configurations within the input configuration of the device to make sure that we have a gap sender, a narrow linear, or a wide linear sender. Now, how you determine what type of device you have from a sender, you're going to be using that histogram to go and have a look and see whether it's a gap sender, as we outlined, or whether it's a wide sender, or whether it's a linear sender. And you should be able to identify that from the characteristics of the histogram that you receive in Prism, and then you can set that up within your configuration. And then similarly for that, you can then plot the graphs for CMAX and VRX for the sender to make sure it is conforming within those limits. So once you've set up your limits for the type of sender that's configured with the packet read schedule, you should then have values that are automatically inserted in the graph that conform to what the maximum limits are for the buffer sizes. So the maximum limit for this wide linear sender is 16 packets for CMAX, and VRX buffer has 720 packets, and those are shown by the dotted line. And in this case, the device falls nicely within those limits. So it is constrained within the expected parameters for the buffering of the packets. And in Inspect 2110, we'll be adding a similar kind of measurement within the RTP metrics. So we're going to be adding CMAX and VRX to the measurement profile that you can analyze within the Inspect 2110. So you'll be able to monitor those values in a similar manner that you can monitor them within Prism. And then finally, I got here a list of kind of a summary of the best practices. So the network is the kind of foundation that you're going to build your IP media network on. So you've got to start with a solid network, and you've got to validate that network infrastructure and design. We've chosen our reference senders and our reference receivers so that we know and become familiar with those type of devices. And that's going to be our main device. If something's going wrong, then we can go back to our reference sender and our reference receiver and connect the signal through that path and verify it works with our known devices. We may not be as familiar with another device that's just been brought newly onto the network, and so we can use those as our reference sender. We've mentioned validating the reference PTP design and using those best practices. And then we're going to determine our monitoring points within the network. So we've outlined areas where you might consider an ingest or transmission to put your monitoring points, but you might also have them dotted around the whole of the broadcast center, looking in QC or edit areas or in the master control room. As you build out your system, you want to define and determine your test plan. So know what you're going to test and how you're going to validate those tests to make sure your device conforms to its specifications. You're going to be testing the PTP infrastructure. So you might decide, I'm going to shut down the secondary network and make sure that all my devices are still locked to my primary network. I might shut down my primary grandmaster and make sure that the device switches to my backup grandmaster. All of those tests you need to build in to your system to test the system and then evaluate your senders and receivers within those processes. We're going to be, once we're installed our system, monitoring by exception. So not getting a whole catalog of errors, but looking at specific errors that are given by simple red, green indications, and then working and down through that process to pinpoint the error and troubleshoot the problem and resolve that issue. So we're taking methodologies to identify problems, troubleshoot those problems, and it's always important to check the basics, to remember those fundamentals, and to make sure that you are validating those fundamentals. Don't forget them. We had a situation the other day where we're trying to troubleshoot why a device wasn't receiving a signal, and we looked at the switch and everything appeared to be okay, and we forgot to make sure that the IP addresses were set correctly for that device in the receiver, and that was our problem. So don't forget to check those basics all the time to make sure that your fundamentals are correct, even when you think that everything should be okay. Just step back a moment and go and check the basics, and then go and troubleshoot further to resolve your issues and prevent them from being a problem anymore. So that concludes the presentation. I'm not sure if we've got any questions.
Yeah, there's one question that came up here, especially on the -7. If you want to go back to the slide, might be a good example. Is the Prism has two interfaces, and you can see the streams from both, which is great. Can you analyze PTP on both and maybe do some comparison to make sure that things are locked and working properly?
So at the moment, the Prism mainly has its PTP on port 1. So if you wanted to look at path 1 and path 2, our normal recommendation is to put one Prism on path 1 and one Prism on path 2 to look at those as a primary source port. In the future, hopefully we'll add it to both particular ports so that you can look at it in the same configuration. But right now, we're looking at and looking at those metrics on each network separately.
Great, thank you so much. And some questions come up about, we're referencing the prior webinars. What we'll do is we'll send out, with this, we will send out the links to the prior webinars that we have. The webinars will be recorded. The recording will be available in about a week. Great, my stumbling was just recorded. The other thing was audio issues that you've seen here. If we had been on a professional media network with the 2110 and also the Prism, we would identify where the audio issues were, lickety split. So, so apologize for the Zoom or internet or CPU issues that were occurring here. If there's any other questions, please feel free to put them in the Q&A. If you don't have any questions, we will be doing another session. If you can go to the next slide, please, which is, next Tuesday, same time. And so please register for that. And for some of the questions that came up about REMIs, remote systems, and timing, this is where we're going to talk about doing basically the baseband timing, remote timing, synchronizing timing across facilities. It's going to be a very interesting architectural discussion that not only talks about timing from a distributed perspective, but how to unify timing within your facility and between facilities, and then thinking about things like, okay, now do I really need time at a remote site that I'm just receiving signals? What can I pull PTP from one site to another, for example? So very interesting discussions on that we're going to get into. Lee's going to lead that one. And then I guess since we're wrapping up here, we only have one more minute. On behalf of the Telestream team, the Imagine Communications team, and from Arista, we thank you very much for participating in this. If you have any questions, please reach out to your contacts. If you don't have contacts within each of these organizations, you can find us on LinkedIn, Facebook sometimes, but mostly on LinkedIn. Feel free. This is a community of people that want to help you be successful, and that's how we all work. We're here to help you learn. As Mike said, we're helping people every day to be successful. We're going to take you from zero to hero as quickly as we can to learn this type of stuff. And again, we'll send out the links to the three prior webinars as well. With that, Mike, thank you very much.
Thank you.
Lee, thank you. And thanks to all the panelists that were answering questions. Have a great day, everybody.
Look forward to seeing you all next week.
Robert, do you want to keep the bridge open just for a few minutes? I see there's still a few questions coming in, so just
absolutely.
Just
Let's see. Somebody's mentioning still having issues. Okay.
So I would maybe just answer that one quickly live. So, I mean, if a device does not allow you to change the domain, it's not a compliant device to the standard, and you just really shouldn't buy that device or go back to that manufacturer to say, please fix your device, because that's that's just unacceptable. So.
Yeah, and that's one of the number one things we see is people have domains configured on the switches or the grandmasters or the end devices differently. And Mike, you touched upon that earlier on the configuration, like on the SNP example.
Yeah, and also, just like, for example, like at the JTM tested event, we explicitly do tests where we change the default domain number because unfortunately we do know over time there are some kind of sloppy manufacturers who have issues like that. So that's why, like, you want to basically go through things like the JTM tested event and select a vendor that has passed that program, because that program tests things like domain numbers and a whole bunch of other things which you should, you have to support, but some people don't. So definitely looking for those JTM tested products is an important thing to help save yourself a lot of headaches.
And the TTL equals 1, that's been one of those ones where you can set it and configure it. And we've landed, I think 1632, is a good number. And that's the number of hops router wise. And if that's one of those things of, hey, it works on my local VLAN, my local subnet, but it doesn't work over here. It must be the network. Well, not always.
Yep.
Any last opportunities for questions?
I think the Q&A now is all that we've answered all the questions now.
Great. Thanks so much, everybody. Again, have a great Tuesday, and we look forward to seeing you next Tuesday for a very informative discussion from Lee on PTP. Additionally, additional questions on PTP and architectures. Oh, here's another one that just popped up from Kurt. Has anyone thought of setting up a training lab where people could get hands-on with these examples? Yes, in fact, Kurt, ping us over here at Arista. By the way, everybody has a lab these days, and we'd love to get you hands-on with the products, do some training, things of that nature. At Arista, we have something called the Arista Test Drive, ATD. That'll get you hands-on from a networking perspective. It's a virtual environment, so even though we can train you on multicast, it's not going to be a live production. We are working on ways together where we can maybe do some simulations for other things like live broadcast. This would be more of a hardware-based thing. This also infers to, and Lee and Mike jump in on this, is how do I start? If I'm going to build a lab, what do I need to have?
Well, so you need one Arista switch, you need one SNMP, and you need one Prism. That's your perfect lab.
And don't forget Inspect 2110.
Yes, indeed. I would say 2 Prisms because with the Prism, you've got that capability, but you may want to put some other things in there, and also 2 SNPs. So look, having the characteristics of looking at it at 2 points in the network, as well as a couple of Arista switches as well, but a couple of Selenium network processors that way you can do your gateway functions, because you've got your SDI to IP, your IP to SDI, so you could play around with your plant today, and then you're going across the network itself. Transmit, receive.
Yeah, and you also want 2 switches, because you do want, for most applications, you do want a 2022-7 network. And so you do want to have the 2 switches so you can properly prototype that out. Oh, and you also need you want 2 grandmasters too. So you want to get 2 SPG 8000 As.
Yeah, that came up in the chat too, which is, can you use the SNP or even the switches as a grandmaster? Lee, do you want to take that, or Mike?
Yeah, definitely for a small network and point-to-point, you can use the SNP as a grandmaster. We've added that capability a couple releases ago. So it's not designed to replace like an SPG 8000 in a main grandmaster for a large network, but definitely for your point-to-point networks or for your sort of small lab networks. The SNP has a good oscillator. It can definitely be used as a grandmaster for sort of smaller installations.
It also gets you into the your baseband synchronization into your PTP. People ask all the time, can you use NTP for time synchronization? The answer is no, it's not as tight timing. Plus, we're trying to get PTP, that very tight timing, down at the endpoints. Another question just came in, a little bit off topic. in a mixed environment, SDI and IP with SPG, GMC, and IP and BB redundancy via changeover. How can we be sure to have the same sync over the whole system? That's next week. You want to know all the answers for next week.
Yes, stay tuned next week. That's one of the things we're covering. That is so an important question.
Have the ACOs in there and all your distribution for your tri-level or your Blackburst, as well as PTP. That's the number one question.
Yeah. Okay, so
right.
so Robert, we're 5 minutes over, and I think we've processed all the questions.
Okay. Well, thanks very much, everybody. Thank you for the team behind the scenes as well for setting this up. And thank you for participating in this. Again, reach out to us if you have any questions at all. Thanks so much, everybody.
Thank you.